Hello and welcome to today's Explainer. I am so incredibly excited to be guiding you through this topic because, honestly, we are looking at a massive leap forward in modern medicine. Today, we're diving into fusion methods in multimodal medical imaging, which is really just a fancy way of saying we're exploring how combining different types of medical scans is absolutely revolutionizing how we diagnose disease. We'll be drawing on some really fascinating recent research to guide us, specifically a 2022 review by Azam and colleagues on medical image fusion and a 2024 study by Lee and their team on how deep learning is taking this whole concept to the next level. Let's get right into it. To kick things off, I want you to consider a seemingly simple question. Can a single medical scan actually show us everything we need to know? Think about it like experiencing your favorite movie. If you only had the audio, well, you'd hear the dialogue, but you'd completely miss the action. On the flip side, if you only had the video, you'd see all the explosions but miss the emotional soundtrack. To really experience the full story, you absolutely need both sight and sound working together. Diagnosing a complex, life-threatening disease is very, very similar. Doctors are basically trying to piece together a critical story, and relying on just one single type of data, it rarely gives them the full picture. All right, let's jump into Section 1, the one-scan limitation, and why single modalities fall short. So, to understand why we need to fuse these images together, we first have to understand the inherent blind spots of using them entirely separately. There is a fundamental divide in medical imaging. On one side, we have structural imaging. These are your CT and MRI scans. Think of these as showing the architecture of the human body. They give us these incredibly high-resolution pictures of rigid anatomy, bone structure, soft tissues, but they don't actually tell us what's actively happening inside those structures. On the other side, we have functional imaging, like PET and SPECT scans. These show us the electricity and the plumbing, so to speak. They reveal active biological processes, cellular metabolism, blood flow, which is absolutely crucial for spotting diseases like cancer. The catch here? They usually have really low spatial resolution. When you actually look at these side by side, the differences is kind of wild. On the left, with those structural scans, the edges of the brain are incredibly sharp. They're so defined. You can clearly see the distinct folds and the barrier of the skull. But on the right, the functional PET scans look, well, pretty blurry and pixelated by comparison, right? Now, they are packed with functionally vital information about brain activity, but visually, it is very, very difficult for a doctor to pinpoint exactly where that activity is happening anatomically just by staring at that one blurry image. Which brings us right to Section 2, fusing for human eyes, combining structure and function. Let's look at the brilliant solution detailed by Azam and colleagues. If a doctor has a razor-sharp map of the anatomy and a blurry map of the metabolism, the logical next step is to just physically merge them, right? And this brilliantly illustrates that exact solution. Look at how gorgeous this is. These are fused MRI and PET brain images from the Harvard Medical Dataset, showing the brain from a few different directions. You can clearly see that the crisp, high-resolution brain structure from the MRI is now acting as this perfect structural canvas, while the color-mapped metabolic activity from the PET scan overlaps exactly where it belongs. A doctor no longer has to guess where a tumor might be located. They can see the high cellular activity perfectly aligned with the brain's anatomy. It's like a giant puzzle coming together. But as you might guess, getting to that perfect image isn't as simple as just stacking two photos on top of each other in Photoshop. Computers have to follow a really rigorous workflow here. First up is registration. They have to geometrically align the two images perfectly, literally matching them voxel for voxel. Second is decomposition, breaking the images down into specific sub-images or frequency bands. Third, they apply fusion rules. This is the complex math that extracts the most important features from both of the images. And finally, reconstruction, mathematically building the final fused image. The ultimate goal here is to add that complementary information without introducing any weird visual distortions that could accidentally mislead a doctor. But, everything is changing right now. Welcome to Section 3, Fusing for AI Brains, the Deep Learning Evolution. As artificial intelligence enters the diagnostic room, we aren't just fusing images for human eyes anymore. We are now feeding raw, multimodal data directly into deep learning models. The Lee paper reiterates our core problem with this powerful quote. An imaging modality alone does not often provide all the information needed to ensure accurate clinical diagnosis. But here's where it gets super exciting. AI doesn't look at images the way you and I do. When an AI classifier looks at a fused CT and PET scan, it's finding hidden synergies, deep statistical correlations, and microscopic patterns between those modalities that are entirely invisible to traditional human analysis. So let's move to Section 4, Levels of AI Fusion, Input, Intermediate, and Output. If you're building an AI to diagnose a disease using multiple data types, you have to decide exactly when and where inside the neural network you are going to actually fuse that data together. Developers generally use three main architectures for this, and they handle data very differently. First, we have input fusion. This one is pretty straightforward. You just stack the raw images together right at the beginning, before they even enter the neural network. It's great if your scans have similar structures. Next is intermediate fusion. Here, the network looks at the different data types separately to extract features, and then merges those features deep inside the network's hidden layers. It is incredible for finding deep, complex correlations. Finally, output fusion. This is where entirely separate AI models make their own independent decisions, and then you just average out their final votes at the very end. This is highly useful if you're combining wildly different types of data. I want to really zero in on intermediate fusion for a second because it is proving to be a total game changer in modern medicine. Imagine the AI has one branch looking at an MRI to understand the physical shape of a tumor, and another separate branch looking at clinical data to understand the patient's blood work. Intermediate fusion allows the AI to extract the shape feature and the blood feature separately, weigh their intrinsic value against each other in real time, and then fuse those specific, highly processed features together before making a final diagnostic decision. And honestly, the numbers totally back this up. Based on the analysis by Lee and colleagues, single-level intermediate fusion absolutely dominates the field. We're talking 51% of all current approaches. It's the go-to method right now because it strikes this perfect balance. It's way more flexible than just smashing raw inputs together at the start, but it's much more integrated than just waiting to average out votes at the very end. So what's the so what here? Why does all this technical architecture matter to you and me? Well, it matters because these AI fusion models are no longer just theory. They are currently achieving superhuman accuracy in diagnosing life-threatening complex diseases right now. For breast cancer, we're seeing models accurately fuse 3D MRI scans directly with a patient's clinical history. For glaucoma, AI is combining physical visual field tests with microscopic OCT eye scans. We're even diagnosing ADHD by fusing the anatomical structure of a child's brain with the functional blood flow of that exact same brain. And for lung cancer, AI is seamlessly blending CT anatomy with PET metabolism to spot malignancies earlier than we ever thought possible. Which leads us to our final stop, Section 5, the future of diagnosis beyond the image. As we wrap up this explainer, it's pretty clear we are standing on the horizon of a massive shift in computer-aided diagnosis. We started by fusing simple images, just so human doctors could see a slightly clearer picture. But today, we're feeding incredibly complex, multi-layered data into neural networks that can see patterns we can't even begin to comprehend. So I want to leave you with something to really chew on. Deep learning isn't going to just stop in images. What happens when we reach a point where an AI model simultaneously fuses your real-time medical scans with your entire genetic sequence, your voice patterns, and your entire lifetime clinical history? We are pointing directly toward a fascinating future of truly personalized, flawlessly accurate medicine. Thank you so much for joining me for this explainer, and definitely keep your eyes on this space. It is moving fast.